A very good morning, one and all. Welcome to the session number 24. LCR Parallel Resonance Circuit. In the last class, we have seen LCR parallel circuit whose current is given as I is equal to epsilon into 1 over R, 1 over R plus J into omega C minus 1 over omega L. It's given as G plus J into BC minus BL. The admittance, which is the reciprocal of impedance, which is modulus Y is equal to square root of 1 over R square plus omega C minus 1 over omega L whole square. The phase difference between voltage and current is given by theta is equal to tan inverse of omega C minus 1 over omega L to the R. The learning objective of this session is to understand LCR parallel resonance circuit. Resonant frequency in case of parallel resonance circuit and the distinction between series and parallel resonance circuit. By the end of this session, you will know what is resonant frequency and the distinction between series and parallel resonance circuit. LCR parallel resonance circuit. We know that the admittance is given as mod Y is equal to square root of 1 over R square plus 1 plus omega C minus 1 over omega L whole square, and its impedance is given by Z is equal to 1 over R minus J into omega C minus 1 over omega L to the 1 over R square plus omega C minus 1 over omega L whole square. With a phase difference, theta is equal to tan inverse of omega C minus 1 over omega L to the R. Now, for a resonating condition, omega C should be equal to 1 over omega L, or omega L is equal to 1 over omega C, then Z becomes R, and that phase angle becomes theta is equal to 90. Theta is equal to 0. Then the current and the EMF will be in phase. Z is equal to R. It acts like a pure resistive circuit. The impedance of the parallel circuit is maximum and hence the current is a minimum. Please note the difference between series and parallel resonant circuit. But the resonating conditions is same for series and parallel, where omega L is equal to 1 over omega C. Then the resonating frequency is given as nu R is equal to 1 over 2 pi square root of LC. Parallel circuit is called rejector circuit or band pass filter because it rejects a particular frequency and accepts others. Now let us understand the diagrams. A plot of current versus frequency for a parallel resonance shows a parabolic in nature, where the current at a resonating frequency is minimum, or Z is equal to. Now if you plot a impedance over frequency at resonating frequency, Z is equal to R, which is maximum. Below the resonating frequency, it acts as inductance, whereas the beyond resonating frequency, it acts as pure inductor. Now the basic difference between series and parallel, there seems to be a vice versa. Now let us understand the variation of the peaks as a function of quality factor. For a quality factor Q, the peak is a broader. With the increase in the quality factor, the sharpness of the peak increases, or I minimum becomes lesser and lesser for a increase in the quality factor. Now to understand the bandwidth between is obtained by, for a given I minimum, multiply by root 2, you will get 2 points omega C1 and omega C2. The difference between the upper and lower frequency is what we call it as bandwidth. So in figure we have seen, with the increase in the quality factor, the sharpness of the curves also increases. The resonant curves gets narrower and narrower. So it able to reject only a particular frequency. Hence it is called as a rejector circuit. The Q factor is given as R over XC, or it can be written as R over XL. It is also defined as omega into energy stored per cycle to the power dissipated. Please note that the quality factor increases with increase in resistance. Now we understood how to find the upper and lower frequency to find out the bandwidth. Now the bandwidth for I minimum multiplied by root 2, you will get two values, which is omega 1, which is given as minus 1 over 2c plus square root of 1 over 2 RC whole square plus 1 over LC. This is the lower frequency, and upper frequency is given as omega 2 is equal to 1 over 2 RC plus square root of 1 over 2 RC whole square plus 1 over LC. The difference between these two, upper frequency and lower frequency, is given by 1 over RC, which is the bandwidth. Now if I multiply these two, omega 1 and omega 2, I will get an expression is equal to 1 over LC, and I know the expression 1 over LC is nothing but omega R square. So this shows the relationship omega R, the resonating frequency, is equal to square root of omega 1 into omega 2. The Q factor is given as R over XC. XC value is omega C, 1 over omega C, therefore R into omega C. The quality factor in terms of bandwidth is given as omega divided by delta omega, that is equal to square root of C over L dot R, where the current in the capacitor is given as Q into I, and in case of inductors is Q into the value of current in inductor or capacitor is magnified by Q, hence parallel LCR circuit is called as current magnifier circuit. Now let us understand the difference between series and parallel resonant circuit. Series resonant circuit is acceptor circuit, whereas parallel resonant circuit is called as the rejector circuit. At resonance, impedance is maximum, which is equal to resistance, but whereas at resonance the impedance is maximum, the impedance is minimum. The current the resonance is given by, in resonance the current is maximum, is given by V over R. In parallel circuit, current at resonance is minimum. Series circuits magnifies voltage, and it is called as magnifier, voltage magnifier, whereas parallel resonance circuits magnifies current, it is called as current magnifier circuit. The series resonance is used in turning circuits to separate the wanted frequency from the incoming frequency by offering low impedance of that frequency, whereas parallel resonance are used to present a maximum impedance to wanted frequency, usually in the plate circuits or values. So this is the differences between series and parallel circuits. So in this session we'll learn, in a parallel resonant circuit the impedance is maximum and hence the current is minimum. The parallel circuit is called as a rejector or band pass filter because it rejects a particular frequency and accepts others. With the increase in the quality factor increases with the increase in resistance. Parallel LCR circuit is called as current magnifier circuit. In LCR parallel circuit, if the resistance increases, quality factor increases infinitely. And an inductor, resistors and a capacitor are joined in parallel with AC source. As the frequency of the source is slightly increased from a resonating value, then the reactance is to inductor increases. With the increase in the frequency of an AC supply, the impedance of the LCR parallel circuit increases at first, becomes maximum and then decreases. If an LCR series circuit is connected to an AC source, then the resonance at the voltage is R equals to the applied voltage. Now LCR parallel circuit, the current always leads the generator voltage. That's all for this session. Thank you.